Yeah, let's get started then. Okay, so today we're very happy to have Xue-Yang from MIT, virtually visiting us, giving a quantum seminar. So Xue-Yang got her PhD from Harvard, and she's currently a postdoctoral fellow at MIT. And Xue-Yang has been working on strongly correlated quantum matters, of all kinds, including strange metals that come out of the SYK model and all kinds of interesting gauge theory that emerges in spin models. So today, Xue-Yang will tell us an interesting story about Emergent QED3 in half-bell flat Chern bands. Right, Xue-Yang, the floor is yours.
Thanks, Tommy, and it's a great honor to virtually visit Cornell and tell you about the recent work on a theory that describe what happens on in half-field Chern bands from periodic modulation of magnetic fields. Let me first say some preliminary background, for this work. We know that if one subjects a two-dimensional, say, electron gas under a strong magnetic field, and then people find that if you measure the transverse electric current response to a magnetic field, characterized by the Hall conductivity, sigma xy, and there will be incompressible state with quantized Hall conductivity, quantized in units of E squared over H. And this nu, nu is typically proportional to the electron filling, the ratio of electron filling with respect to the magnetic field strength. Initially, we discovered this plateau where nu is quantized in integer, so-called integer quantum Hall states. Later, once we tune up the magnetic field, people also found that there are incompressible states, the plateau with fractional nu, written in terms of P over Q. An exotic effect in this fractional quantized plateau states is that there is fractional excitation, which is a part of a physical, say, electron. So to see the existence of such fractional excitation, one can do this thought experiments by threading a magnetic flux, time-dependent magnetic flux, phi of t, adiabatically, basically as some magnetic solenoid, right? During this adiabatic process, there is electric field along the azimuthal direction induced. By definition of this Hall response, we have electric current in the radial direction. So when we adiabatically increase the flux from 0 to 2 pi, the system go back to itself. 2 pi flux is invisible to the electrons, which can be seen by a phase transform in the electron wave function. So when the flux reaches 2 pi, the Hamiltonian is equivalent to the original Hamiltonian. However, during this process, there is a charge that gets pulled in or pulled out by the radial current, right, induced by the Hall response. And the amount of charge is proportional to the Hall conductivity, sigma xy. So in the case of fractional Hall conductivity, which here we use the 1/3 as an example, we know that we have isolated an excitation that carry a fractional amount of charge. So these fractional quantum Hall states nowadays have found its counterpart in a lattice system. Basically, fractional quantum Hall is, as we say, is characterized by this Hall conductivity proportional to the filling, right, to nu. And the fractional chain insulator is a lattice analog of fractional quantum Hall, in that we also have a fractionally quantized Hall conductivity sigma xy. However, the difference is the sigma xy is not necessarily that doesn't necessarily have to be proportional to nu, which effectively can be thought of like you can have a part of your electron density as attached to the lattice sides, and then the remaining parts of the electron, they participate in the formation of a fractional quantum Hall states. So in this case, we don't need a very large magnetic field, right, to reach this fractional filling. So it might be a good way to realize fractional quantum Hall and the fractional excitations, like without the need of a large magnetic field. And indeed, these fractional chain insulator states, they have been observed in the so-called Moiré system. So I believe like you are more or less familiar with Moiré system. And like, I mean, yeah, we have like the experimentalists at Cornell, like is one of the pioneers on Moiré system. So when you take two different crystalline alignments and they form a long wavelength period modulation called Moiré pattern, and people first like realize this twisted graphene, like Moiré system for graphene, and we have a say superlattice constant at the scale of 10 nanometers. And theoretically, it was predicted that at certain magic angle, the kinetic energy of the electrons are quenched. So so-called like you have flat band. And like in 2018, it is found that superconductivity and correlated mod insulating states arises in this Moiré system. And under a application of magnetic field, so here is the plot of the local compressibility measurement, where the more radar it is, the more incompressible the system is. So in particular, those red fringes in the plot, right, as a function of the filling and the magnetic field, these red fringes denotes these incompressible states, and the slope of these fringes is proportional to the conductivity. And by carefully measuring the slope, people characterize that there are both, say, this integer slope, which characterize, which is a integer quantum Hall states. And here, yeah, with the inclusion of lattice effect is the, like, say, the Chern insulator phase. Interestingly, there is also the red fringes with a fractional slope. And they also, like, the Hall conductivity is not proportional to directly proportional to the filling. So they have these lattice analogs, namely the fractional Chern insulator phase is also realized in twisted graphene. And yeah, of course, there is also a competition between, say, other symmetry breaking states, say charge density wave, and this fractional, say, Chern insulator. So this is like manifestation of the competition or interplay between the band topology and interactions and spin valley degree of freedom in Moiré graphene system under magnetic field. And in another Moiré system, like so-called transition metal tetrachlorogenides, people also find similar, like Chern bands, like analog of quantum Hall states, and here, which is the anomalous Hall state, also as a witness of the existence of topological band in this Moiré system. Right, so Moiré system, like the biggest advantage is that it's highly tunable, right? As we model the electron as hopping in a Moiré potential, in the Moiré superlattice. And almost every parameter, like the kinetic energy, the interaction energy, the Moiré superlattice, they can be tuned. And even like the material combination, we have a rather diverse choice, right? So it's highly tunable and give us an window to explore the interaction effects and the competition between, say, kinetic interaction and other factors. And people are most excited about the gap state or the symmetry breaking states, right? As we introduced in the previous experiments, like charge density wave or like this Chern insulator, fractional Chern insulator states. While the normal states, like is less studied. So by normal states, I mean they, like say, they preserve the symmetries and or like they are gapless states, right? And here I want to talk about some non-trivially gapless states arising in a sense, it's also a Moiré system, like from the modulation of magnetic field, and how we can like design using this periodic modulation to design towards novel phases, namely this fractional Chern insulator phase. Yeah, so here is the outline of my talk. We consider subjecting a Dirac material, namely the low energy Dirac, the electrons behave as if they are relativistic electrons. And we're subjecting such Dirac material under a magnetic field. And upon applying a periodic modulation at the length scale of the typical Moiré superlattice, like also 10 nanometer scale, for example, the states like low energy theory that describe such system. And I'll first introduce the methodology like the composite fermion and how like it successfully described this fractional Chern insulator, fractional quantum Hall states, and in particular the half field Landau level case. And then I'll motivate in the composite fermion picture how the quantum electrodynamics emerge under a periodic modulation of the magnetic field. And further we'll see like the proximate fractional Chern insulator phases and other phases upon adding further a electrostatic potential to the system. Yeah, so as we mentioned, here, like previously, people were looking for the evidence for the existence of topological bands or flat bands in Moiré system. And here we sort of start with a topological flat band arising automatically, naturally from this quantum Hall states from the Landau level. And then we see, like, we want to motivate that a gapless Dirac or like quantum electrodynamics arises in this topological flat bands. Yeah, so our setup is to consider the surface of a topological insulator, where we have like the electron dispersion at the surface is described by the relativistic Dirac equation. And upon applying a magnetic field, the electron, low energy electron dispersion will be transformed into forming discrete Landau levels, as shown by these black either dotted or solid lines. And importantly, there is a zero mode, degenerate zero modes at the like charge neutrality point, the blue line. So if we tune the electron, like Dirac electron filling to be at charge neutrality, then after forming the Landau level, the zeroth Landau level is automatically half filled. Yeah, so we first focus on the case of a half field Landau level and what happens if you add, say, periodic magnetic field. And actually, even for the continuum, like for the uniform magnetic field case, at half filling is already a very interesting state. So initially, people like in gallium arsenide, people find that at a half filling, there is a exceptional metallic state in this electron gas. And later, other interesting states at a higher half filling is also found, like say third order or even non-abelian states, they are observed. So here we want to ask, what if we go beyond the continuum description of the Landau level, namely we add some Moiré patterning by periodic modulation, right? How this this band effects from the Moiré patterning will affect the description, and whether any interesting physics can arise from this periodic modulation of magnetic field. So to study this problem, we employ a tool so-called Composite fermion. And the Composite fermion, the physical picture can be understood by like attaching some vortex, like basically some small magnetic flux one can think of to the electrons, and then forming a composite fermion. So to preserve the statistics of the fermions, we attach like 2 flux quanta to each electrons. Then the effective magnetic field felt by the composite fermion is like screened by the magnetic flux attached to the fermions, right? For example, if we consider the plateau at 1/3 filling, originally it means like the electron density is 1/3 of the physical magnetic field strength. And the effective field felt by the composite fermion, right, is reduced by twice of the electron density. And the simple algebra shows that now the effective magnetic field is equivalent to the composite fermion density. So namely, the 1/3 fractional quantum Hall states now is translated as an integer quantum Hall states for the composite fermion. And in this way, the plateau, like incompressible state found at this 1/3 filling is naturally explained. Right, so again, I want to remind you that we ultimately want to engineer towards fractional Chern insulator, where like the sigma, like the signature is that the sigma xy is not directly proportional to the filling anymore. Okay, so now let's further see how composite fermion can be used to study the 1/2 field Landau level. As we mentioned, it's an exceptional metallic state at half filling. So again, at half filling, the effective magnetic field by this algebra, because the 2 flux quanta attached to the composite fermion exactly screen the physical magnetic field. So the composite fermion actually, they didn't see any effective magnetic field at the mean field level. And naturally, they form a composite Fermi liquid, which describes the metallic state at half filling. And there is a very important symmetry at half filling, which is the particle hole symmetry. So to understand how the particle symmetry acts on the composite fermion, it's useful to introduce this dictionary, the mapping between the physical electron and the composite fermion picture. So it's sort of a particle vortex duality. And what we need to know is that the magnetic field density is mapped to the particle density and vice versa. So like the 2 sides is the magnetic field density and the particle density is a reciprocal relation from the 2 pictures. So the action of the particle symmetry, right, it's preserve the physical magnetic field, and it sends the electron density with a minus sign. So translated to the composite fermion language, it means the composite fermion density, which is proportional to the physical magnetic field, stays the same. However, the effective like magnetic field felt by the composite fermion is mapped to the physical electron density and changes sign. So from the action of the particle-hole symmetry from the composite fermion side, looks as if it's a time reversal symmetry, right? It preserves the rho, the density, but it changes the sign of the effective magnetic field. So what we need to know is that particle-hole symmetry acts as if it's a time reversal symmetry for the composite fermion. So now we are equipped to further investigate what happens once we add a periodic modulation part for the magnetic field, namely the B1 part, which average to 0. So one preliminary thing is if we take a free electron under a periodic magnetic field, one can show exactly that the 0 modes is still exactly degenerate. Namely, we still have a perfectly flat band at 0 energy. So this is due to more profound, like topological reason. It is this exact flat band, and it's also a Chern band due to the quantum Hall physics that enable one to enhance the interaction effects, just as like the flat band in the Moiré system, right? Okay, so we asked, like now in general, one should include, say, interaction effects. What is the theory, like low energy theory that describe half field Landau level under a periodic?
I apologize, I have a real quick question. So
Sure.
this result that adding the periodic magnetic field doesn't break the degeneracy of the Landau level,
Right.
That's true for a weak magnetic field, or is that true for any magnetic
For any magnetic field.
Arbitrary, and is the periodicity important?
You can even have like arbitrary modulation of magnetic field. It doesn't have to be periodic. Yeah, as long as the total magnetic field, like integrate over the entire system, is non-zero, you will have a degenerate 0 mode that's proportional to the total magnetic flux.
Thank you very much.
Yeah, thanks. Right. So next I'll focus on like the main result of our work is like the low energy theory upon a periodic modulation of magnetic field and the proximate phases and the numerical and experimental implications. Yeah, so as I already promised, will motivate the emergence of quantum electrodynamics in 2+1D in this setup. And so why is quantum electrodynamics in 2+1D interesting? So our physical world is described by 3+1D quantum electrodynamics. And it's a weak coupling theory characterized by the fine structure constant at the order of like 1.01. And we have a well-defined, say, electric charge and photons, these particles, which form the foundation of our physical world. And when you reduce the spatial dimension by 1, the things like the landscape changes drastically. So the quantum electrodynamics in 2+1D is usually a strongly interacting theory and without well-defined particles. And out of certain limits, say the large NF limit, like its fate in the infrared is inconclusive. Say whether there will be a vacuum excitation of certain fermion bilinears, or like whether like the monopole effects will cause confinement, etc. Like we don't have a like conclusive phase diagram for QED3. So it will be of great interest to simulate the quantum electrodynamics, a strongly interacting theory, like in condensed matter system. And maybe we can even like predict the property of such theory from the simulation or from its realization in condensed matter system. Yeah, so now let's see, using the composite fermion picture, how the quantum electrodynamics could arise. So if we remember the dictionary, right, the magnetic field density and the particle density, they are mapped from this particle vertex duality. And then a periodic magnetic field is mapped to a periodic modulation of the composite fermion density. Or equivalently, like it generates a chemical potential felt by the composite fermion with the same periodicity. So this periodic magnetic field will scatter the composite fermion by the periodicity of the vertex lattice. And by the way, so we took the vertex lattice forming by the periodic magnetic field as a triangular vertex, like due to its nice geometric property, and it's also natural, like for the abricosive vertex lattice formed by, say, type 2 superconductors. So now let's imagine like the states felt like the band structure of the composite fermion, how it evolves, right? So without the periodic modulation, like when the B1 is 0, we have a field like Fermi C states, right? And the Fermi surface is a circle. And once we add some periodic magnetic field, as we say, it scatters the composite fermion by the like reciprocal lattice vector of the triangular lattice, which the Brillouin zone is a hexagon. So it gradually deforms this circular Fermi C. And more importantly, the gapless states along the Brillouin zone, they will be gapped out due to like basically level repulsion, right? Like because now the states, like pair of states in the Brillouin zone, they are connected by the scattering of the periodic magnetic field, and so in generally they will be gapped. And gradually, if we tune up the modulation of the magnetic field, the Fermi surface will be more deformed, and importantly, most of the states along the Fermi surface will be gapped, except we still have a particle hole symmetry, which squares to -1. And as we already see, it acts as a time reversal symmetry. It's an anti-unitary time reversal symmetry for the composite fermion. So this condition satisfies the application of the Kramers degeneracy, which means that at certain high symmetry points that are invariant under this particle hole symmetry, right, the degeneracy of the band structure is guaranteed. So indeed, at the Brillouin zone edge, we have 3 such high symmetry points that are invariant under the action of particle hole symmetry. Namely, they are the so-called M points, like the middle points of this hexagon edge. We showed both like by perturbation theory and numerics that when the periodic magnetic field, the periodic modulation is comparable to the uniform component of the magnetic field, then we have this emergent Dirac dispersion for the composite fermion. So to tune the chemical potential to be at the like this emergent Dirac cone, right, at the Brillouin zone edge, this corresponding to filling all the states inside the first Brillouin zone, and which corresponding to 1 composite fermion per vertex lattice unit cell. So now we have a emergent like Dirac fermion, which is different from the physical Dirac electron we start with. Here is the Dirac fermion in the composite fermion picture, right? As we say, this needs to, like the condition it requires is that 1 composite fermion per vertex lattice unit cell, which by this equation of motion corresponding to 2 flux quanta per vertex lattice unit cell. The low energy theory in this case, as we say, consists of 3 Dirac fermion, chi I. Also, we need to include a small a U1 gauge field, which is a statistical gauge field that enforce the flux attachment to the composite fermion, like attaching two flux quanta to each composite fermion. So the ADA term, the mutual transaminance term, says nothing, but the composite fermion and the physical electron, they see each other as the vortex. So they are captured by this mutual transaminance term. And so in this way, we have a,
I think, may I ask a question?
Yeah.
Actually, it's actually related to the previous slides. So when you get these band structures,
right.
Do you start with some dispersion and then you add a chemical potential that depends on R, and then these just come out? What was the starting?
Right. Yeah, so the starting point is we actually use the Dirac composite fermion formulated by Danson. Yeah, so the starting point is Dirac composite fermion, like located at the origin, the gamma point. Like we will like say take some universal Dirac velocity, right? And then we add some like chemical potential with the characteristic Fourier component of the reciprocal lattice vector. Yeah.
Got it. Thank you.
Yeah. Right. So we have the composite fermion forming Dirac cone interacting with the emergent U1 photons, which is exactly like the quantum electrodynamics. Albeit now we have three species of Dirac fermion. And for the theory to work, we emphasize that there is a hierarchy of the energy scale, which is the delta is the energy gap from the zeroth Landau level to the first Landau level. So we want the energy gap to be much larger than the interaction energy and much larger than the bandwidth. So at the free electron picture, the bandwidth is exactly zero. We have exactly flat band, right? So this is we require this energy hierarchy for the composite fermion picture to be valid, right? To avoid the Landau level mixing, and also to the Dirac composite fermion picture is valid below the energy scale of the Coulomb interaction. Yeah. So if you take a characteristic, like say magnetic field of say 5 Tesla or 10 Tesla, the requirement of 2 flux quanta per unit cell means the vertex lattice constant is again like at 10 nanometer scale. So it's comparable to the typical Moiré superlattice scale. And we want to emphasize now that the quantum electrodynamics is a stable phase, a robust phase. And the condition to realize such a gapless phase is that we need 2 flux quanta per unit cell, and then we need a particle symmetry, right? That guarantee the gaplessness of the composite fermion. As we mentioned, the fermion mass, they are forbidden by the particle symmetry. Curiously, at this emergent Dirac cone for the composite fermion, we have a emergent particle symmetry. This is not to be confused with the physical particle symmetry, but it's really a particle symmetry for the composite fermion that sends the composite fermion filling F to 2 minus F, which is emergent in this effective QED description, QED Lagrangian. Right, so now let's think of the proximate phases from the QED3. So as we already mentioned, the particle symmetry is important to guarantee the Dirac dispersion for the composite fermion. And to break the physical particle symmetry, we can naturally add a electrostatic potential V1. And for now, we want to consider a commensurate V1, like V1 has the same periodicity as the vertex lattice. And one can show both numerically and perceptively that this commensurate electrostatic potential actually opens the gap for the low energy composite fermion dispersion. So the upper panel describe the Dirac cone, right? With this particle symmetry, the 3 Dirac cone. And now upon adding a electrostatic potential, we show in the numerics that a gap, which is the same for all three composite fermion Dirac cones is opened. because this electrostatic potential preserves the symmetry, say translation and say rotation of the vertex lattice. So we open up actually a singlet gap. Yeah, so and if we fix the electro potential V1, the average to be 0, then on average we are still at the charge neutrality. So the phase diagram here we plot focus on the charge neutrality, and we show that, say, if we only add periodic part of the magnetic field, like focus on the horizontal axis, right? As we mentioned, once we tune up the periodic modulation to above a threshold, we enter into this QED3 phase. And now if we add the vertical axis, which is the periodic electrostatic potential, and we gap out the composite fermion, and the system enter into some incompressible state. And we show that these incompressible states, they are the fractional Chern insulator state. So like they have this fractional Hall conductivity of 1/3 and 2/3 respectively. And moreover, as we say, the total filling is still fixed at 1/2, right? So this means that the Hall conductivity is not proportional to the filling, right? We fix the filling, but we have a fractional jump of the Hall conductivity. So from this fact alone, it's enough to show that the incompressible state will be the fractional Chern insulator. And to show that like a very it's a not rigorous argument to show that we have a jump of 1/3 Hall conductivity from this periodic patterning of the electrostatic static potential. Again, we use this particle vertex mapping. So the physical electron current is mapped to the electric field felt by the composite fermion. So basically, the physical electron density is felt by the composite fermion as the magnetic field. And now, when the electron move, like the composite fermion may feel a Lorentz force, which translated as a effective electric field, and vice versa. The physical electric field is mapped to the current of the composite fermion. So upon gapping out the composite fermion, right, the two sign of the mass, they corresponding to a Hall response jump by 1. Basically, the Chern number jump by 1 for each composite fermion Dirac cone. And in the physical electron picture, we know the electric current and the electric field, they are exchanged. So the Hall conductivity for the physical electron, they jump by an inverse of the jump in the composite fermion picture. So basically, you conclude that the Hall conductivity jump is a fractional 1/3 jump from the 3 composite fermion Dirac cone. Yeah, so again, we emphasize that we realize a fractional quantum Hall transition at fixed half filling. So the proximate phases, they are the fractional Chern insulator phases. Yeah, so if you are interested in for the experts, we can also very straightforwardly see it in the field theory description. You integrate out the composite fermion and have a fractional Chern-Simons fractional level Chern-Simons term, and we can get the Hall conductivity as 1/3 and 2/3 respectively. Right. So and the physical consequence for the quantum electrodynamic phase is that so if it can be realized relatively simple in an experimental setup, right, under periodic magnetic field subject some Dirac material. And if we reach this quantum electrodynamic phase, the compressibility will be linear in temperature rather than constant as the composite Fermi liquid. And the conductivity is related to the photon polarization in the quantum electrodynamics. So it should be a universal number, say the DC conductivity, which is an intrinsic property of the quantum electrodynamics. And Another interesting property is that the flavor mass of the composite fermion, they correspond to the physical charge density wave, and at a characteristic momenta, which is the momentum difference of the different Dirac cones of the composite fermion. And all these different flavor mass, they are unified by the emergent like flavor symmetry between the three Dirac cones. So the charge density wave correlation at this particular momenta, they have power law decay, and the power law, the exponent is the same for this different momentum, like the different corresponding to like different combination scattering between the composite fermion Dirac cone. For the experts in the QED3, we also have another class of critical operator called monopoles, which can be thought of as some instanton event that change the flux of the U1 field by multiples of 2 pi. And here, this monopoles, which is seen by the composite fermion, is charged. The easiest way to understand is that, again, the composite fermion and the physical electrons, they are related by the particle-vortex duality. So the vortex seen by the composite fermion will be the physical corresponding to some physical combination of the physical electrons. So the monopoles, which is seen as the vortex by the composite fermion, is charged and is automatically forbidden by charge conservation. So this means the quantum electrodynamics is stable, and we don't have to worry about like confinement from the monopole proliferation. So this will also be an ideal platform for numerical simulation of the QED. So like say for exact diagonalization, we can say upon tuning the electrostatic potential, right, at two parts, like the different sign of the electrostatic potential, we realize the fractional quantum pulses, which when putting on a torus has the ground state degeneracy of 3. And at the critical, like at 0 electromagnetic potential, we realize this quantum electrodynamics with a gapless spectrum. So I guess in the interest of time, I'll quickly flash like the doping case. So previously we all focused on charge neutrality case, right? We add a periodic modulation of the potential, electrostatic potential. And what if we add a uniform electrostatic potential, right? Like namely dope the system. So again, the uniform electrostatic potential V0 will be seen as in the composite fermion picture as a uniform magnetic field B0, and the composite fermion Dirac cone will form Landau level. So by few like integer multiples of the Landau level, we can again land in some incompressible state. Some similar like calculation tell us that these incompressible state also have fractional Hall conductivity, which actually form like land on like some sequence in the like so-called Jane sequence. Again, like the phase diagram for doping is that at some particular magnetic field value that corresponding to 2 flux quanta per unit cell, we have the quantum electrodynamics. And then upon doping, if we adjust the electromagnetic field correspondingly, we will have these incompressible fractional Chern insulator states. Right, so in summary, we consider the subjecting a Dirac material under periodic magnetic field, which can be thought of as a half field, a Chern band from the Landau level. We show that at particular like magnetic field strengths that's corresponding to 2 flux quanta per unit cell, and also with this particle symmetry at charge neutrality, the system can be described by quantum electrodynamics, which is a strongly interacting conformal field theory. And by tuning the electrostatic potential, a fractional phase, fractional Chern insulator is realized. And experimentally, one similar setup is realized, and it's also an ongoing experiment, is by putting the topological insulator in proximity to a type 2 superconductor, which naturally form the vertex lattice. Although there, the vertex lattice has half of flux quanta per unit cell, as the vertex in the superconductor is quantized in like half flux quanta. So alternatively, to realize the 2 flux quanta required, we can use like this micromagnet arrays to give a periodic modulation of the magnetic field. And there are also possible interesting states from our more exotic states originating from this QED theory. Like one can, for example, consider the pairing instability for the composite fermion, which may form some non-abelian states. This half-field Chern band formulation may also be relevant to the correlated physics found in the twisted bilayer graphene, right? The incompressible, like the compressibility plots I showed at the very beginning. Like there, like one may also think of if these states can be realized in twisted bilayer graphene. So the take-home message is like we can have interesting gapless states in Moiré system, and here this gapless state is also in some sense topological in that it arises in topological Chern bands, and we show that like the Moiré patterning, say of magnetic field and of electrostatic potential, serve as some tuning knob for designing towards this fractional Chern insulator phase, where we don't require like careful engineering of say quantum geometry or quantum metric, because this is automatically satisfied in the flat Chern band from the Landau level in magnetic field. So that would be the end of my talk. Thanks.
Thank you, Xue-Yang. So any questions from the audience? Maybe you can just speak to that.
Hi, Xue-Yang.
Hi.
So I missed this. Why are these 3 Diracs pinned to the endpoint?
Why there are 3 Diracs?
Why you have these pinned to the endpoint?
Right. So it's because, as we say, there is a particle-hole symmetry that enforces the Primus degeneracy between like one state and its particle-hole conjugate. And so when it's in the Brillouin zone, it's only at this high symmetry point where they are invariant under particle symmetry. Particle effectively act as time reversal, so it sends the momentum k to minus k. So it's only at this high symmetry point where k and minus k are equivalent do we have this Primus degeneracy. Do we have a like degenerate state?
See, then why can't you have Dirac at k points?
So k points, the minus k point is like k prime, right? It's an inequivalent point.
Oh, I see.
Right.
But then how about the gamma point?
Yeah. In gamma point, there is also a Primus degeneracy. Although like at gamma point, the energy is different, right? It's different than the 3 Dirac at the Brillouin zone edge. Like this 3 Dirac, they are at the same energy is enforced by some rotation symmetry. They are connected by rotation.
Yeah, I see. Then the question is that how is like so it seems that you have 2 scenarios. One is that you have a Dirac, you can have a Dirac at gamma point.
Yes.
Or you can have 3 Dirac at like end point. Like which state do I get? Like how much is that determined by like your specific Hamiltonian of the composite fermion and like what's robust?
Yeah, so yeah, that's a good question. So in general, say if you start from the Dirac composite fermion formulation, it's a Dirac cone located at the gamma point, right? And then if we add the chemical potential, at least if we consider the chemical potential with the Fourier component only as the first reciprocal lattice vector, like the smallest reciprocal lattice vector, right? The most natural state is that you have so the 3 Dirac cone at these endpoints, they are always degenerate. The question is whether you first reach say the 3 Dirac cone at endpoints, or you may reach, say, some Dirac cone at gamma points at higher energy. And we conjecture that that the Dirac cone at gamma points at some higher energy, higher band, requires like 2 composite fermion or like some higher filling of composite fermion to be reached. So yeah, that's in general, if you don't have very fine-tuned or very highly designed like chemical potential or like say the physical magnetic field, in general, that should be the natural case, right? It's a deformation of the original Dirac composite fermion band structure.
I see. Thank you.
Thanks.
Other questions? I do have a question. So I guess you said why you chose the triangular lattice for the vortices, but let's say I just create these magnetic field using some pattern micromagnets, and I could do anything, I suppose. Is that, and then maybe I have different number of Dirac cones at different places if I go for
right. So for example, in square lattice, so again, the Dirac cone has to be at certain high symmetry points because they are guaranteed by the particle symmetry, right? Or the time reversal symmetry. So in, for example, square lattice, if we have the square, the Brillouin zone is also a square Brillouin zone, and typically we can guarantee one Dirac cone realized, like say at again some M points or like the corner, right, of the square Brillouin zone, and they are like by we have emergent 1 Dirac cone guaranteed. We don't have this nice property that the rotation on triangular lattice naturally guarantees a 3 Dirac cone. They must be at the degenerate at the same energy level. For square lattice, we do have Dirac cone at these high symmetry points, like the corner or like the middle points of the edge. But it's not guaranteed that they are at the same energy. So we can reach like 1 Dirac cone QED. And this will realize some, like say, adding electrostatic potential, this will realize a Hall connectivity jump of 1 rather than 1/3. 1/3 is related to the fact that they are 3 Dirac cone in the composite fermion language. Yeah, so it's a slightly less interesting. You realize an integer Hall connectivity jump.
And also, can you give the 3 Dirac cone separate mass of different signs? And how easy is it? Or is it possible to do that?
Is it possible to what?
Oh, I think in your analysis, you assume that the 3 Dirac cone takes the same mass, right? Like the same sign of the mass. Can I individually address them? Open up mass gap, of any sign that I choose separately for each color.
Yeah, so if you break the rotation symmetry, then in general, the mass for the 3 Dirac cone could be different. And yeah, if say if you have two opposite sign of mass, and the other Dirac cone can stay either gapless, which in the case is still as a quantum electrodynamics, or if the other Dirac cone is gapped out, then you realize a Hall conductivity jump of 1, right? Effectively, if the two of the mass sign they cancel, and yeah, we realize a conductivity jump of 1, like basically from sigma xy to 0 to sigma xy to 1 jump. Yeah, so these are other scenario if you break rotation symmetry.
Questions? Okay, I guess if not, let's thank Xue-Yang again.
Thank you.
Yeah.